This video is on periodic trends and how we explain them, so how we know for sure that there are these patterns in the periodic table. There are, I believe, 4 or 5 different trends that you do need to know, and they're going to be completely new for you. So this video might be a tad long, but I'll try and go through it quickly to make sure that you're not spending too much time listening to me. So the first thing we're going to look at is Lewis diagrams. So hopefully you remember that this includes the symbol for the element and only and only the valence electrons. So if I look at hydrogen, hydrogen only has 1 valence electron, so we draw 1 dot. Lithium as well only has 1 valence electron, so 1 electron in its outermost shell. Remember that. So the valence electron is in the outermost shell. If you look at something like calcium, calcium would have 2 valence electrons in its outermost shell. So that's how we draw the Lewis dot diagram. And we're going to use, you guys did a whole periodic table with these, so we're going to use these to explain some of the trends or some of the patterns that we see in the periodic table. So I'm sure you know how to fill in the rest of those. You can do that on your own. And we're going to start looking at what a trend is. So a trend is also known as a pattern. And some of the patterns that we've seen already are things like elements within a group have the same number of valence electrons. Now this is actually a really important concept. Chemical behavior, so how these elements react with other elements, is really based on how many valence electrons it has. Therefore, it is expected that chemicals within a group will have similar chemical behavior. There are slight differences between the elements of a group, since each element has a different number of shells and a different atomic number. But what we see, even though all of these things are true, what ends up happening is we have these variations or trends that can be seen in the periodic table. So the first trend we're going to look at is chemical reactivity. So how easily do these elements react? Chemical reactivity tends to be high in group 1. So high over here on the periodic table, and high in group 17 over here, and then lower towards the middle of the table. The noble gases are the least reactive group because they have a full and stable valence shell. And within a group of metals, reactivity increases moving down the group. So as I go down a group in the metals area, so that's sort of on this half of the periodic table, as I go down, the ones at the bottom of a row are more reactive than the ones at the top of a column there. And then within the nonmetals, the opposite is true. The ones at the top are the most reactive, and the ones at the bottom are the least reactive. The second trend we're going to look at is atomic radius. So the atomic radius is exactly what it sounds like. It's the size of the atom, measuring from the center of the nucleus to the valence shell. It's measured in picometers. And 1 picometer is 10 to the negative 12 meters. You don't really need to know that, but it just gives you an idea of how small these atoms actually are. So the trend here, I still have these marks. The trend here, we go from left to right and going down a group. So we'll look at the first one. From left to right across the period, the radius decreases. So as we go this way, you can actually see in this picture that the atomic radius is getting smaller and smaller and smaller. So here's the big thing about this video. You have to know what the trend is, and you also have to be able to explain why. So this is my quick explanation. Why do we see the atomic radius decreasing in size as we go across? And here it is here. As the number of protons increases, so if we go from lithium to beryllium, to boron, to carbon, to nitrogen, to oxygen, to fluorine, to neon, we're increasing the number of protons each time. So lithium has 3 electrons, beryllium has 4, boron has 5, etc., etc. But we're not increasing the number of shells. So we have more protons in the middle of the nucleus. That means that the electrons are pulled closer to the nucleus because there's more positive charge in the nucleus. So those shells that are shells of electrons around the nucleus are going to be pulled in closer. The trend going down a group, so as we go down, this is the second trend, the atomic radius increases. So again, the big thing is that you know the trend, but also that you can explain why. So why does this happen? As we go down a group, we increase the number of shells. So if I look at my first group here, hydrogen has 1 shell, lithium has electrons in 2 shells, sodium has electrons in 3 shells, potassium, and so on. Increase the number of shells as we go down the group. So as the number of shells increases, the electrons that are farther away are basically not held so tightly by the nucleus, so it is able to get bigger as you increase the number of shells. So here is a picture of the general trend in atomic radius. So as you go down a group, it increases here, and as you go across a period, it decreases, it gets smaller. All right, oh, get rid of those arrows. There we are. Our next trend is ionic radius. This one might be a little bit tricky, but hopefully you'll still get it. An ion, remember, is an atom that has lost or gained electrons, so that its outermost shell can be completely full or completely empty. So the trend is that positive ions are smaller than their negative or their respective neutral atoms, and that negative ions end up being bigger or larger than their respective neutral atoms. So again, you have to know what the trend is, that's this statement here, and then you have to tell me why. Why does that happen? Why are positive ions smaller than their neutral atoms? Well, let's have a look. For lithium, if I have an electron floating around in this outermost shell here, what I'd like to do to become stable is I'm going to lose that electron and become Li1+. Well, when I lose that shell, that valence shell is now empty, so now my atom is actually smaller. The other thing on top of that is that when I take an electron away, I've got more protons and electrons, and those protons can pull in those electrons a lot closer and make the atom smaller. Now let's look at the trend for negative ions. And it says again here, negative ions end up being larger than their respective neutral atoms. Now I don't have a picture of that on this slide, but you can sort of see what will end up happening here. Let's see if I can draw in a little corner here. So again, why does this happen? Answer is here. The electron-electron repulsion increases when an electron is added, and therefore the radius increases. So if I have something like fluorine, fluorine has 7 valence electrons around it. If I add in an extra electron right here where my X is, those electrons are all negatively charged and they're trying to stay as far away from each other as possible. So what'll actually end up happening, just to create room for that extra electron, is they'll all sort of expand and come out a little bit. Oops, I'm sort of going off my screen. All the electrons will open up a little bit to accommodate for that extra electron so that we minimize the electron-electron repulsion. Because remember, all electrons are negatively charged. They're going to push away from each other and repel. All right. Our next trend is ionization energy. So ionization energy is the amount of energy required to remove an electron from an atom or ion. And basically what we end up with is a positive ion. Okay, so anytime you're taking an electron away, that is called ionization energy. The first ionization energy is the removal of the outermost electron. The second ionization energy will be the removal of the next outermost electron. The third ionization energy will be the removal of the next. So for example, something like boron has 3 valence electrons. If I remove the first one, the amount of energy required to do that is called the first ionization energy. Then I have to remove a second one. That would be the second ionization energy. And the third one, that would be the energy required to take away that third electron, would be called the third ionization energy. So the trend across a period is that as we go from left to right across a period, the ionization energy. So again, remember that you need to be able to explain why. So my why, I think you figured out by now, is always listed in blue here. So my ionization energy increases. That means it's tough. It's tougher to remove an electron. If energy increases, that means you need more energy for something to happen, which means it's harder to do. So as we go across a period, the number of protons will increase, and the electrons are more strongly attracted to that positively charged nucleus. So therefore, there's going to be more energy required to remove an electron. So think about the difference between lithium and fluorine. So lithium has 1 valence electron, fluorine has 7. If we remove an electron from lithium, that's going to be a heck of a lot easier to do than to remove it from fluorine, because the electron in lithium is going to be farther away from the nucleus, whereas the electrons in fluorine are going to be much closer to the nucleus. So that's, let's see here. There we go. Now we're working. And then the trend going down a group is that the ionization energy decreases, which means that it's easier to remove an electron. And that's because you're increasing the number of shells. So as the number of shells increases going down a group, electrons are farther away from the nucleus, and therefore less energy is required for them to be removed. So again, I have a quick little chart if you want to add this in on your notes. Here's the trend for ionization energy. It decreases or becomes easier as we go down a group. Ionization energy increases or becomes harder as we go across a period. All right, electron affinity, and then we're almost through. So electron affinity is the energy that's given off when an electron is added to a neutral atom. So this is sort of the opposite kind of ionization energy. So your trend going from left to right across a period, electron affinity increases. So that means as you go from left to right, now this is weird because even though it's still energy, the electron affinity increases, which means it gets easier to gain an electron because of where the energy is placed on the chemical reaction up here. But you don't really need to know that. As long as you know the trend and you can explain it to me, you're good. So again, why does this happen? As the number of protons increases across that period, the electrons are more strongly attracted to the nucleus, which means the other thing is we have bigger atoms, and then as we go across a period, the atoms get smaller, which means if I want to add that extra electron in, it can get a lot closer to that positively charged nucleus and add itself in much easier than something over here. The last trend then for electron affinity going down a group is that electron affinity decreases or gets harder. And that's because as the number of shells increases, the electrons are farther away from the positively charged nucleus and less energy is released when an electron is gained. Again, here's the general picture for electron affinity. Going down a group, it decreases or becomes harder. Going across a group, increases or becomes easier. All right. I'm going to introduce you to a brand new topic here, and I think this is the last trend that we have to look at. But before I talk to you about electronegativity, which is our last trend, I want to show you this slide about bonding. I don't know if you learned about this in grade 10, but basically all bonds are going to share electrons in some way, shape, or form. Sometimes they're shared equally, sometimes it's very unequal. So these pictures here in my boxes are basically pictures of electrons in and around some nuclei involved in a bond. So as you can see, I'm going to start with an ionic bond way over here, this lithium chloride. And as you can see, the electrons are really here or here. There's a real distinction between those two areas. And that's because your chlorine gains an electron and is negatively charged, your lithium loses an electron and is positively charged, and those electrostatic charges attract each other and it holds itself together in an ionic bond. So this is a very unequal sharing of electrons because the chlorine literally takes the electron completely from lithium. Now let's go over to, I'm going to skip the one in the middle, I'm going to go over to H2 here. You can see here that there's no distinct region between these two atoms. So here's an H here and here's an H there, and there's no real separation. That means that those electrons are really floating around in between those two atoms very equally. Okay, that's what's called a covalent or nonpolar bond. Now if we look at HCl, what's going to end up happening is, again, you have your H and we have our Cl, and you can see the area around Cl is bigger because Cl has more electrons than hydrogen, so that sort of makes sense. But what ends up happening here is that these two electrons in between are actually really close to the chlorine. And that's what's called a polar covalent bond. So now this is a totally new concept, so we are going to talk about it a lot more in class and in other videos. But what we end up here is because the electrons are actually kind of much closer to chlorine than to hydrogen, we get what's called a partial charge. So this little weird looking kind of S is actually a lowercase letter d. We use delta, a Greek letter. So that ends up being a little bit negative, or we call it a partial negative charge. The H ends up being a little bit positive, or we call it a partial positive charge. The point I'm trying to make here is that the bonding electrons are shared in each compound, but are not always shared equally, and that Greek symbol delta indicates a positive charge. For now, that's all you need to know, because I am going to talk a little bit more about this in the next slide and in other videos. But that's sort of where the concept of electronegativity comes from. So here's the actual trend that you guys need to know. Electronegativity is the ability of an atom to attract electrons when bonded to another atom. So I call it sort of hogging electrons. So if you've ever had to, say, share a blanket with somebody, I remember when I was a kid, I used to share a bed with my sister when we shared a room, and one of us would always hug the blanket more than the other, and it was usually the bigger one because we were stronger. So the same thing's going to happen here. If something is more electronegative, that means it has a stronger ability to hold on to those electrons, and it's going to hog the electrons within the bond. So the trend is from left to right across the period, the electronegativity increases. So that means these elements are much better hoggers. So that's because the atomic radius decreases along the period, increasing the attraction between the electrons in the nucleus, and therefore increasing electronegativity. Yikes! Lots of words in there. Let me show you this other trend. Going down a group, electronegativity decreases, and then I'll explain it a little bit more, and then we're done. As you go down a group, electronegativity decreases because when you go down a group, your atomic radius is going to increase because of extra shells, and that decreases the attraction between the electrons and the nucleus, which will in effect decrease its electronegativity. So basically what's happening here is atoms with high electronegativity can hog electrons more. Electrons with low electronegativity will tend to give up those electrons. So this picture here is fluoromethane, and it's actually the same thing. One is just sort of the structure of it. The other sort of shows you the electron density. And you can see the red area here. That means it's got a very high electron density. So that fluorine that's over on the side right here is hogging those electrons. So there are two electrons here between the fluorine and the carbon that are being shared, but fluorine is more electronegative, so it's going to hog those electrons and pull those electrons closer to it. I'll explain that more in class. Oops, sorry, where did I go? There we go. There's the general trend for electronegativity. I am going to, like I said, explain it more in class because sometimes it's easier if I actually show you with my hands how this works. But the awesome thing about electronegativity is that it's actually on your periodic table. So you can look up a value for electronegativity. It might be 1.3 or 3.6 or whatever it is, and you can actually see if one is higher or lower than the other. So you don't need to memorize this trend, but you do need to understand why it works. The key terms in this video were basically the 5 different trends that you need to know on atomic radius, the nuclear charge and how many protons are in that nucleus, the ionization energy, electron affinity, and electronegativity. I know they're all very new for you, so we'll spend lots of time in class going over those concepts.